Welcome to this Maths Minis video on modelling exponential growth and decay. To start with, let's take a look at exponential function graphs. Now you need to know how to sketch y equals e, so let's just write this down. So y equals e to the ax plus b plus c. And the best way to do this is step by step. So the first thing we want to do here, step 1, is find where the graph intercepts the axes. So the y-axis is when x equals 0. Okay, so the y-axis is at x equals 0. So in that case, the y-intercept is simply going to be y equals, placing this x here with 0, we just get y equals e to the b plus c there. Okay, and for the x-axis, this is at y equals 0. So that's at y equals 0. So the x-intercept is at e to the ax plus b plus c equals 0. And this is just simply an equation which we know how to solve. But note here that if c is greater than 0, the graph does not cross the x-axis. Okay? And in this case, we can rearrange this then to find the x-intercept here is x equals the natural logarithm of minus c minus b all over a there. Okay, but like I said, you could just obtain this by rearranging here. So we'd minus the c first, we'd then take the natural logarithm of both sides, we'd minus the b, and then finally we'd divide by a there. Okay, that gives us our x-intercept there. Step 2 then, we want to find the asymptotes by looking at the behaviour of the graph as x tends to plus infinity, positive infinity, and minus infinity. So, if we note here, let's do this in a different pen colour then. So, as x tends to positive infinity, well, in this case, y equals e to the ax plus b plus c will tend to infinity. This will tend to infinity if a is greater than 0. Okay, so that's if a is greater than 0. However, it will tend to c. Okay, so it will tend to c if a is less than 0. Okay, and as x tends to minus infinity, so as x tends to minus infinity here, what would happen here? Well, again, y equals e to the ax plus b plus c. Well, this here will tend to c. This will tend to c if a is greater than 0. Okay, and it will tend to infinity if a is less than 0. So this tends to infinity if a is less than 0. Okay, and finally, all we do then is we put all of this information on a graph, and we can use this to plot our graph. So make sure to take a note of all of these points, and let's just clear this now just so we can see an example of what this would look like. What you should get is something that looks like this. Notice we have our x-intercept here, like we said, x equals natural logarithm of minus c minus b divided by a. We have the y-intercept here of y equals e to the b plus c. And we have our asymptote here of y equals c. Just a quick note here that this is for a being greater than 0. The graph would just simply be the other way around if a is less than 0. So that gives us everything we need there for exponential function graphs. Let's move on now to take a look at natural logarithm graphs. You also need to know how to sketch y equals, so let's just write this down here, so y equals the natural logarithm of ax plus b. Now the best way to do this is step by step. So step 1, we find where the graph intercepts the axes. So the y-intercept here, or where it cuts through the y-axis, is at x equals 0. So for the y-axis, this is at x equals 0. Okay, in that case we just simply replace x here with 0, and that just simply gives us our y-intercept here at y equals the natural logarithm of b. Okay, So hopefully nice and straightforward. And for where it intercepts the x-axis then, that is when y equals 0. So if we note that here, that's at y equals 0. So in that case, we just replace y here with 0, so we get the natural logarithm of ax plus b equals 0. But what we need here is x equals. So in that case, we take the exponential function of both sides of this equation, and that gives us ax plus b is equal to e to the 0, and anything to the power of 0 is 1. So ax plus b is equal to 1, and we just now solve for x, which clearly would just be 1 minus b, so we'd minus the b first, and then divide by a. So therefore, x is equal to 1 minus b all over a there. So that gives us where it intercepts the axes. Step 2 now, we just find the asymptotes by looking at the behaviour of the graph as x tends to plus and minus infinity. So first let's consider if a is greater than 0. So if a is greater than 0, then as x tends to positive infinity, so as x tends to infinity, well, y equals the natural logarithm of ax plus b tends to infinity. Okay, it tends to infinity. And x can decrease until ax plus b equals 0. So there's an asymptote. There's an asymptote here at x equals minus b over a. Okay, where y tends to negative infinity, or minus infinity there. And let's consider then if a is less than 0. So if a is less than 0, well, as x tends to minus infinity, then y equals the natural logarithm of ax plus b tends to infinity. So this tends to infinity. Okay. And x can increase, so x increases until ax plus b equals 0. So there's an asymptote, x equals minus b over a. Okay, where y, this is where y tends to negative infinity. Okay. And then finally, all we do is we mark all of this information on a graph and use it to plot our graph. What we should get is something that looks like this. Notice we have our x-intercept here at x equals 1 minus b over a. We have the y-intercept at y equals the natural logarithm of b. And then we finally have our asymptote here at x equals minus b over a there. Okay, so we should get something that looks like this. So that gives us everything we need there for natural logarithm graphs. And finally, let's take a look then at modelling exponential growth and decay. Most real-world problems about exponential functions involve either something increasing, which is an example of exponential growth, or decreasing, which is an example of exponential decay. The maths in these problems is not new, but it's not trivial to interpret what the questions are asking. So let's take a look at this example here. And it's split into two parts. Part 1 here, we just want to find the value of a from this given equation, and then part B, we want to find the half-life of the particle. So let's start with part 1. So we want to find a. So how would we find a here? Well, we need to use some conditions that are given to us in the question. And what we're told here is that the particle starts with a radioactivity of 500. So what that's telling us is when t equals 0, R, the radioactivity, R is radioactivity, this is equal to 500. So using our equation here for R, if we just simply substitute our value for R and t in, we will be able to find A. So therefore, 500 is equal to A e to minus 0.05 times by t, which is equal to 0. Okay, and this here would give us e to the 0. So we get 500 is equal to A e to the 0. Okay, and remember, anything to the power of 0 is equal to 1. So I get 500 is equal to A times by 1. So therefore that just tells us that A is equal to 500. Okay, and that simply gives us the solution there to part 1 to find A. Now for the second part here, to find the half-life of the particle, well, remember the half-life is when the radioactivity has halved. So at R equals, so part 2 here, this would be when R is equal to 500 divided by 2. So that would be 250. So in that case, using our equation for R here, that means we're looking for 250 is equal to AE, but remember we know what A is, that's 500, so that's 500 E to the minus 0.05 T. So what we're looking to do here now is solve for T. So to start with, we can divide the left hand side and the right hand side by 500. So that would give us E to the minus 0.05 T is equal to 250 divided by 500. Okay, and this right hand side here clearly simplifies to just give us a half. So what we get then is E to the minus 0.05 T is equal to 1 over 2 there. So here now we're looking to find the value of T, and as we have the exponential function here, that means we're going to need to use the natural logarithm. So here now, if we take the natural logarithm of both sides of this equation, what I get then is minus 0.05t is equal to the natural logarithm of a half. Okay, and remember we're just looking for t then, so therefore to find t, if we just finish this at the top here, a different pen colour so we can see it clearly, so therefore for t then, so we're going from this line here, well we just want t, so we just need to divide by minus 0.05. So t is equal to minus the natural logarithm of a half divided by 0.05 there. Okay, and if we evaluate this on our calculator, what you will find is 13.9 there. Okay, and that gives us the solution to the second part there. So that gives us everything we need there for modelling exponential growth and decay, and that concludes this Maths Made Easy video on modelling exponential growth and decay.